Welcome. In this video lecture, I am going to talk about what is the master production schedule and how we can link this master production schedule with the aggregate production plan. So let's first of all discuss what is the aggregate production plan. So basically, when we are seeing the aggregate production plan, that is usually developed for the product family or a product group. So let's take the example of a washing machine. Okay, so if I'm saying that a particular company is going to plan that how much they should produce of the washing machine in the month of January, how much washing machine they should produce in the month of February, and so on. And even we should know at on those particular months what are the capacity we have available. So based on that, we are trying to develop the aggregate production plan where we're trying to find out the trade-off between the production rate, mean production quantities of particular product group in a particular month. Okay, what would be the workforce we have, what would be the inventory. So we are trying to find out the trade-off between those, you can say, the decision variables in which we are interested. But right now in this lecture, we are mainly talking about the master production schedule, which is basically the disaggregation of the aggregate production plan. So when I am saying the disaggregation, because right now over here we were talking about the washing machine, that is a product family. But in a washing machine, how many model A we are producing, how many model B we are producing, how many model C we are producing. So that means we are talking about the specific end item or end product. So when we are developing the end item product schedule or a plan, that is called as a master production schedule. So how you can define the master production schedule? That is basically a time phase plan, okay, which specifying how many and when the firm should produce a particular end product. So in a nutshell, we can say that the master production schedule is what is to be produced and when it is to be produced. Okay, so we can call it as a lot size, right? So over here, let me give you example how we can link the aggregate production plan with the master production schedule. Suppose here we have the aggregate production plan, okay, which is called as sales and operation plan. So we said that in the month of January, February, March, and April, so we have developed the plan, whatever the plan we have developed in the aggregate production plan. So in the month of January, we said that demand is this, February, March, and April. And the production we have planned is this one. The ending inventory we have planned at the end of that particular month is this one. Okay, now let's take the example. Let's say we are going to disaggregate the month of March demand. That is this one, which is basically the 4,000. Okay, and because we are talking about the product family, so over here we are saying that push mover, okay, power movers, and lawn tractors. Okay, so that is basically the end product. So which is in short, we can say that product A, B, and C. This one. So we are going to aggregating this particular demand, and we are saying that the product A we should produce because this is monthly. Now we are developing based on the weekly basis. Okay, so we decided that out of this 4,200 product A we are going to produce in week 1, 250 we should produce in week 2, and 3 and 4. Okay, so we are disaggregating with respect to the demand. So you can also say that the proportion of this product A demand out of this 4,000. Similarly, the proportion of product B demand out of this 4,000 is that we should produce 400 in the week 1 of product B, 500 over here, 600 over here, and 700. Similarly, product C, right? And then based on this end product demand, we should develop the a master production schedule. That means in which particular week we should produce, and how many we have the initial inventory, how much we should have the ending inventory in that particular week. Okay, so right now I'm not going to talk about how we can manually calculate this master production schedule, but right now what I am going to focus on that how we can develop the mixed integer linear programming model for this master production schedule problem, and then based on that mixed integer programming model we should generate the master production schedule uh, solution, right? But first of all, remember that in the reality, when we are talking about the linkage between the aggregate production plan and the master production schedule is, so whatever we have developed the aggregate production plan, that must be aligned with the master production schedule must be aligned with the aggregate production plan. Okay, what does that mean? That means if we are saying that we should produce 5,000 unit in the month of March, so the sum of these production units as well as this. So overall the sum should be equal to the 5,000. So that means the MPS should be aligned with the aggregate production plan. So if it is not aligned, that we should adjust the master production schedule. However, it should be aligned with the aggregate production plan. So in reality, so most oftenly the master production schedule is unlikely to match exactly with the master production schedule. So what we are going to do is we will play hit and trial and then try to meet the master production schedule with the aggregate production plan. So in order to this imbalance, so what we can do is either we can have the safety stock of that particular item, okay, in order to deal that imbalance between supply and demand, or you can say capacity and demand. We can schedule the overtime production, we can uh, develop the outsourcing and so on. Okay, so in a nutshell, the MPS focus is to generate the production schedule, which means what kind of product we are going to produce in month one, what kind of product we are going to produce in month two, and so on. Okay, and the focus is, instead of only the product family, we are talking about only the end product, and the time horizon is usually either the weekly or the daily basis. And what would be the product mix, which product mix mean how many we should produce product A, and how many we should produce product B, and how many should we produce product C. However, our production schedule cost, the total cost should be minimized. So let me show you the mix and teacher model for the master production schedule. Okay, that is basically this one. So the model we have is that is for the master production schedule is the mixed and integer linear programming model. So this model is also known as multi-item single level capacity lot sizing problem. So multi-item mean, or you can say the multi products, because we have the multiple end product. The single level, which mean we are not considering the bill of material. Okay, we are only considering the end product. And capacity mean we are going to consider the capacity constraint as well, and then we are interested to find out the lot size. So in order to develop the mixed integer linear programming model, so in order to represent the multi-product, so that means we have the index, the notation index J, that J is representing the set of end products. Okay, and if there are the multiple resources, you can say the multiple machine there, those are going to produce this end product, then we can represent that index with K. So K is representing the set of shared resources, or you can say the machine which has the limited capacity. T is representing the set of time periods. Okay, and then we have certain parameters and the data. Okay, so c capital CKT is representing basically the available capacity of the resource during that time period. AJKT is basically representing the amount of capacity of the resource K consumed per unit of the product I while producing. Okay. Similarly, SJKT is representing basically the setup time. It is while to produce the product J. DJT is the demand of the product J in during time period T. PJT is a unit production cost. This is a setup cost. This is a holding cost. And so that means when we are talking about the parameter and that data, so this data set we must have before going to calculate the master production schedule with the help of mixed integer linear programming. So we should know this particular information. And our decision variable are, that is the quantity we should produce of product J in time period T, how many inventory we have in of product J in time period T, and this is the binary variable whether we should set up this product J in time period T or not. Okay, so using these notation we can develop the mixed integer linear programming model. That is, we are going to minimize the total cost. Okay, what is the cost? This is basically the total production cost, because pj is representing the unit production cost. This is the quantity of product j we are producing in time period t. So this is the total production cost, this is the total setup cost. So this is basically uh, uh, per unit setup cost of product J during time period T. This is the binary variable whether we are setup uh, taking setup of the product J in that time period or not. Okay, so this is basically the total holding cost. This is carrying cost per unit, or you can say holding cost per unit of product J during time period T. This is the inventory. And subject to, we have the three types of constraint. The first constraint we have the inventory balancing constraint, which you can also call as the demand and supply constraint, or simply we can say is the demand satisfaction constraint. And that is basically the inventory we have in the last time period for product J, okay, plus the quantity we are going to produce in this particular time period of the product J, and what are the demand of the product J during this time period, and how much ending inventory we have at the end of the period T. Okay, and the second constraint is basically talking about so whenever there is a setup, so we can produce as much as possible, because this mjt is the big M number. Okay, so basically this constraint is going to link the production with the setup variable. Whenever there is a setup of that product, okay, so we can produce as much as possible, but we have a certain capacity restriction. So that capacity restriction is over here. Okay, so over here I am saying this is a total production time. This is basically the total setup time. This must be less than or equal to the setup, sorry, the capacity we have of resource K in during time period D. So remember that over here we are considering the time. This is a total production time, because this is the per unit time to produce product J on resource K during time period T. So this is the QJT is the production quantity of product J we are going to produce during time period T. Because we are considering them in a time, as well as this is a setup time, so the capacity we should consider in the time. Okay, that is available capacity, right? Instead of in the quantity, because over here we are considering the time. And the three decision variables we have, that is the QJT and IJT. So these two set of variables must be the positive, and whereas YJT is a binary variable. So now we have get the understanding about the mixed integer linear programming model for developing the master production schedule. Now let's discuss how we can implement this mixed integer programming model in the OPL CPLEX, and then with the help of that OPL CPLEX we are going to solve this model. So for that I'm considering the test instances of this one. Okay, so where we are considering that uh, the number of time period we have, basically we are developing the production schedule for the next 4 time periods. We have total number of products 4, and resources are is equal to 1, so which means our k is equal to 1 over here. So the k is 1. If the k is 1, so that means in a model there is no need to define k, so that means only we have one resource, which means one machine. So that means majorly we are going to use GNT, because we have multiple product, multiple period. So the unit production cost for all the product is 10. They have given the setup cost every particular product, holding cost for every particular product, and demand they have given. So the row is basically representing the product. Okay, so this is the product one in month one. In the first time period demand, this is first product in the second time period demand, and so on. Okay, similarly this is a second, this is a third, and this is a fourth product. And then we have the setup times. Okay, Similarly, we have a setup time for the particular product. Okay, how much time they are taking to set up for that particular product. Similarly, this is the production time per unit. This is the capacity we have. Okay, so based on this test instance, we are going to develop this mixed integer linear programming model on a OPL CPLEX. So first of all, we are going to define the indices. So that means we need to define J and T, and where J is representing the product, T is representing the time. So as you can see over here, so here we have the indices, that is basically double slash indices is indicating the comment. Okay, and then we are defining int is the data type, and j is equal to 3 dot, which is indicating we are going to define number of product in the data file. So over here I have defined the data file, which is 4. Okay, the next is I'm going to define the number of time period. So I'm saying int t, that is the time. Okay, again 3 dot are indicating that the data is in the data file with t is equal to 4, and range is period is from 1 to 4. So once we have defined the indices, that is product as well as time period, the next thing we need to define is basically the unit production cost, because the unit production cost for all the product is 10. So that's why I'm not using the array. I'm simply using a Decision variable, which is I'm going to define float unit production cost is equal to 3 dot, and that's why over here I'm defining the unit production cost is equal to 10. The next thing we need to define is basically the setup cost. This production cost we have already defined. We need to define setup cost and holding cost. So for the setup cost, because in the data set they have given us that the setup cost against every product is different. So that's why I'm using the one dimensional array. Okay, so for that, how we are going to define float setup underscore cost, this is products. Okay, because against every particular product we have a different setup cost, right? And then we have mentioning 3 dots in the data file, how we can define this one. So remember that when we are in a model, we need to tell whether it's a float type or a int type, but in the data there is no need to mention the data type. So only we are writing down the name of the variable, which is a setup cost. So over here we are mentioning setup cost is equal to, so this data value. So first against first product setup cost, second, third, and fourth, which we are mentioning over here, that is the first, second, and third, and the semicolon is indicating the end of this line code. Next, we are similarly going to define the holding cost against every particular product. Okay, so this is a holding cost, right? Similar way like the we have defined the setup cost. Next, we are going to define the demand. So as we know that based on the data set, they have told us that so first product against time period 1, 2, 3, 4, second product against time period 1, 2, 3, 4. So that means we need to tell the two-dimensional array in a OPL whenever we are going to define. So it is going to be a two-dimensional array. One is for the product and the other is for the time period. So that's why I'm going to define float demand. The first is representing product, which means the row is representing the product. The column is representing the time period. Okay, 3 dots, and how we can define is that is with the help of two array. Okay, two-dimensional array. So this is basically how we are going to define the demand. Next, we are mentioning the production time, which means we are talking about this AJKT. Okay, so because the K is 1, so there is no need to mention the K. So JT. So if we can see over here, so they are saying that whatever the time is, every time we are producing a particular product, okay, so that is the difference. So only against a particular product. So that means we need only a one dimensional array, that is basically the production time against a particular product, and the time it is going to take is that is this one 2131. Okay, Similarly, we have the setup time, that is again one dimensional array. Okay, we are going to use to define this one, which is the setup time, right? And then we have the capacity, that is again a one dimension, and the capacity is based on the time period, which is constant. So that is, we are considering this one. Okay, and lastly, because in the model we have MJT, which is indicating the big M, so that's why we are defining int big M. And over here, I am defining the setup time, the capacity, and the big M number. So once we have defined the indices, we have defined the parameters and the data. The next thing we need to define is the decision variables. Okay, so how many decision variables we have? We have three. Two are the continuous type, another one is the Boolean type, or you can say binary variable. So first of all, I'm defining the production quantity. So as we know that dvar is a keyword of the OPL programming language, the optimization programming language, which means define variable. Okay, what type of? That is float plus. Float plus means it is a continuous positive decision variable. Okay, and this is whatever the name you want to take, that is the name of the variable, which is the production quantity. And for product j, okay, so for every product as well as for every time period. Similarly, we are defining the inventory variable. Okay, so dvar float plus inventory products. Okay, so either you can write down periods over here. Why I'm using the 0 to t? Okay, because that is the range. Although we have 1 to t, so why I'm saying 0 to t? Because I need to deal with this particular variable. Okay, so that's why I'm defining over here. So there are other way to deal this kind of situation as well, but right now I am considering this option. So I am saying that when we are talking about the time period in the inventory variable, it must start from 0 to t. Okay. Whereas the product setup time we are defining because it's a Boolean type, so that's why we are saying dvar Boolean, and this is the production setup time for the product and time period. So once we have defined the indices, we have defined the parameters and the data, we have defined the decision variables. Now we are going to define the objective function. Okay. So what I am going to do is I am basically separating each type of cost. So this is the total production cost. This is the total setup cost. This is basically the total holding cost. So first of all, I am going to calculate the total production cost. So when I'm going to calculate some expression, so for that the keyword is DEXPR, which is the define expression. What kind of the data type we are using, which is a float. So that is a total production cost is going to be sum j in product and t in period. That is for this one. Sum j for the first summation and t for the second summation perspective. And the equation is the product per unit production cost multiplied by the production quantity. So the per unit production cost we have stored in the unit underscore production cost multiplied by the decision variable of the production quantity for product j as well as t. So this j is in product, this t is in period, right? So whatever you are mentioning over here, so that's where this j is in product, so this is the product. So t in period, so this is the period, right? Similarly, we are okay. So now we are defining similar way the total holding cost. So for that again, I'm defining define express float total holding cost, some j in period, t in period, holding cost, because the holding cost for every particular product is different. So that's why I'm saying holding underscore cost j multiplied by the inventory variable. Okay. So right now t in periods, right? Okay. So the next one is basically we are defining the total setup cost, like the production cost and the holding cost. And at the end, we need to sum it up. Okay. So we are saying that the total production cost is going to be equal to define express float. The total cost is equal to the total production cost plus total holding cost plus total setup cost we have. Okay. Okay, next we need to define our model. The next model is going to be minimizing this total cost. Okay. Okay, so the total cost is going to be the sum of this total production cost, the total holding cost, the total setup cost. So that's why we are saying define expression, float, the total cost is going to be this one. So this is my objective function. So I want to minimize this total cost. So minimize the total cost subject to, okay, the first of all, I need to mention what is my first time period initial inventory. So basically I'm dealing with this particular variable. So for that I am saying for all j in products, which mean for every product, okay, I am mentioning that the initial inventory is equal to 100. So that means for product 1, product 2, product 3, product 4, I am supposing that it is equal to 100, and this is the name of the constraint we are mentioning for this initial inventory. Okay, and then we have the next constraint is the inventory balancing constraint for all j and for all t. So this is for all j in product, t in period, and this is we are mentioning inventory j t minus 1 exactly. That is the math model we have. Okay, so we are translating into this inventory balancing constraint. Okay, the next constraint we have that for all JT, the production quantity must be less than or equal to the big M number multiplied by the Boolean variable, which means whenever we are set up the product J in a period T, then we can produce as much as we can produce. So that's why we are saying for all J in product T in period. Okay, so this is again the name of the constraint. Then we are saying the production quantity, which is QJT, must be less than or equal to the big M multiplied by the setup variable. And lastly, we are mentioning the setup constraint. Okay, so for that, I am saying for all j in product, and this is then t in period. Okay, so there is no need to use this for j. Okay, because we are summing up for the every particular. So only we need to use over here is for all t in periods, because we have only one resource, that is k is equal to 1. So for every t, so that's where we need for all teen periods. Then this is the name of the constraint, and then we are saying this is the total production time. So how we can calculate that one? That some Jane products, we are saying the production time of that we are consuming for to produce particular product J multiplied by the production quantity, and this production time we have already defined over here, which is basically this one, right? And then we are saying that plus we have the sum gene product. This is basically the total setup time. So again, the setup time multiplied by the setup variable. So this was the total production time, this was the setup time, must be less than or equal to the capacity of that particular time period, okay, against every particular time period. Okay, so that means the model is completed. Now, if I can want to solve it, I can solve it. How we can do that? Simply drag and drop the model file in the configuration as well as the data file in the configuration, and right click and run it. But let's discuss that how I want to see the results. So for that, I am basically performing the post process. So after the constraints block, okay, we are going to executing the post processing block, and this is basically we are saying execute. This means write line. Okay, this the function is write, ln mean line. Okay, so in double quotes whatever you want to write. So I am saying that show me the total production cost which we are going to calculate with the help of this one. Okay, so I am saying total production cost equal to, so show me that number, as well as show me the holding cost, as well as showing me the total setup cost, right? In addition to that, I am also performing some pre-processing. What does the pre-processing mean? So this is a pre-processing, you can say, block. So I am executing the time limit. Okay, that is basically I am saying that how much time basically I want to set that CPLEX if it is able to solve the particular model within this particular time period. Fine. If it is taking longer than that, then just stop after this upper time limit, okay, and show me the results. So how you can do that? Simply, this is a block we are saying executing time limit. So you can write down cplex, write dot, and then once you press the dot, you will see that there is a list of variable. If you are not seeing that, you can also use dot and then press the tab key. You will see this list. So over there, if you can see that I am just searching the time, TILIM. Okay, so that is a time limit. Otherwise, you can also search from this particular list. Okay, let me show you. Okay, so you will find out this thing over here. So just write down TILIM, which is a time limit, is equal to, so how many seconds. No, usually in the setting file I have mentioned the seconds, right? So by default it is also a seconds. So you can mention the number of seconds over here. So that is basically, if the Cplex is able to solve this problem within this time limit, fine, show me the results. If it is taking more than this time, just stop the solution and give me the result whatever it has found within this time limit. Okay, now this is important. That is basically the entire model is basically, you can say, dealing with the main block. So what I am saying that this main block is this model, this OPL model. What does this mean? This OPL model mean whatever the model we have written down over here. Okay, so I am saying this is a keyword basically of the Cplex. This is this OPL model dot generate. Okay, so that mean I am saying that generate this CRUD model test instance. Okay, and which mean I'm saying that solve this model if the cplex dot solve, okay, which is basically if cplex dot, then we have a function called solve, okay, and we are saying that if it is equal to 1, which means if it is able to get the optimum solution, run these commands. Else, if it is not able to get the optimum solution, just write down there is no solution the Cplex has found, which means no solution. Okay. But if it is able to find out the optimum solution, first of all, I am defining a variable called var. This is basically a JavaScript language. Okay, var, which is basically a variable, right? And then I am saying that in this basically variable is equal to new, this is the output file, which means the result is going to be saved. That is the function, and where I am going to store that file, that is I am basically mentioning the entire address where I want to store this one. So the basically the name of the file of the solution is this one. Okay. And remember that when you are giving the path, so it should be the front slash. Okay. There should be no backslash. Okay. Otherwise it is going to give the solution. So which means once this model is going to be solved, the solution report is going to be saved over here, whatever the path you have given. And then I am saying offline, okay, of file output file, okay, this o file mean output file dot write line, okay, and I am saying this model, okay, that means this OPL model dot print solution, which mean print the solution of this model. Okay, and what kind of things we want to print, that mean entire solution, plus I also want to see the CPLEX, how much time it has taken to solve this problem. So that's why I'm mentioning CPLEX dot get CPLEX time. Okay, and then I am mentioning the total production cost, that is again this OPL model, okay, which is that is this one, this entire model. This is a keyword, and then I am mentioning the total production cost, similarly holding cost and the setup cost. And then I am saying the output file dot close, which means I just want to get these answer. After that, it is should be close this file. Okay, and then I am mentioning that the variable obj, which means the objective function, is going to be calculated. Okay, get the objective function value, which means the total cost, and then show me that result against this line. So this is the line whatever you want to write down, and in this particular variable we have the objective function value, as well as also show me the time, right? And then this model dot processing, what does this mean? Post processing mean this egg model, this block, which is this execute block. Okay, so if now I run this one, okay, if I'm going to run this one, you can see that there will be, so it is taking some time. Okay, so this is some taking some, so over here I can see the results. Okay, so you can also check that we can also getting this answer in the script log. So that means this is indicating the total cost, this is how much time it is has taken, this is a production cost, holding cost, setup cost. So obviously sum of this one is a total cost. So in the engine log it is basically showing me the different algorithms. In a statistics, this is basically the objective function value and so on, right? And now if I am going to that particular folder where we have developed this OPL project, as you can see that here we have that file, which is the output file, which means the solution file. So over here you can see that the objective function answer, this is the decision variable answer production quantity, which is saying that so there will be no first product we are producing the time period 1, time period 2 we are not producing anything. So product 1 is going to be produced 39 unit in the time period 3, and then in a time period 4 is 99. Similarly, how much inventory we have of a particular product in a particular time period, in which period we are going to set up the machine or not for that particular product or not. And then we are mentioning how much time the CPU has taken to solve this problem, and then at the end we are mentioning the total production cost, holding cost and the setup cost. I hope you got the idea how we can solve this master production schedule problem using OPL CPLEX. So thank you so much. See you in the next video.